Okay, students, we're starting a new topic. We're going to talk about forces for a long time now. And I know I said this with your last topic in the last videos where I said, hey, you guys, this is really like one of the most important topics of the whole 2-year sequence because you're going to be using kinematics all the time. Well, I'm going to say it again, and probably this particular unit of the course is actually more important than kinematics because we really do use forces probably even more for 2 years, okay? So let's go ahead and get right to it. Remember, you're going to be relying a lot on what you already know about forces and what you've learned about forces in your previous classes. So let's get right to it. So the first thing that I want to do with you guys is to kind of show you how to identify the basic different kinds of forces that we encounter all the time, and also obviously start off by defining exactly what a force is. Okay. So the most basic definition is that a force is something that can move, deform, stretch, rotate, or compress something. It's also something that can cause a velocity change, and that's important for us in terms of our analytical and technical definition of a force. And if it causes a velocity change, it causes an acceleration. And in the most simple case, a force is simply a push or a pull. The SI unit for a force is the Newton, of course, and it's a vector quantity, so I have it drawn here as, in this most general sense, capital F as a vector, okay? So just a couple of examples of forces, okay? Here's a rocket taking off from the surface of the Earth. Because it's accelerating upwards, there's obviously a force acting upwards, which I have labeled here, okay? In this case, there's a picture of a guy pushing a blue car to the left, okay? And because the car is starting from rest, it's obviously accelerating in that direction. Therefore, the force that he applies on the car is in that direction. And you know from Newton's second law that the acceleration of an object and the net force applied are in the same direction, and we'll talk about all that in much more detail, okay? You should know that there are only 3 known types of forces. This might be a little bit surprising for you. I'm going to talk about different kinds of forces, but when you get right down to it, on a very basic level, there are only 3 known types. Number 1, gravitational. Number 2, strong nuclear, and these are forces that occur within the nucleus between nucleons, which are neutrons and protons. And something called the electroweak forces. These are electromagnetic forces and what are called weak nuclear forces, which we will study later, okay? Almost all forces that we deal with are of the number 3 type, the electroweak, okay? So here's Newton's second law, which is F equals ma. Remember that a body accelerates in the direction of the net force applied. Or in other words, an object moves in the direction in which it's pushed or pulled, which is, of course, common sense, which, of course, is one of the most beautiful things about the class you're taking, is that it's common sense. Physics is like trained common sense, okay? All right, so some of the most common forces that we encounter all the time. Most are number 3. The first one I'm going to talk about is gravity. Okay, weight, which is also called the force of gravity. It can be W or F sub g. Okay, it's the force of gravitational attraction between an object and a planet or another more massive body. Okay, and I'm going to tweak that definition very slightly in just a minute. Okay, you know that W equals mg. Weight is mass times the acceleration due to gravity. Okay, I've got them whenever I introduce formal vector equations. I'm going to have the actual vector symbol over the variable. Otherwise, if it's a bold-faced variable, bold-faced letter, that also obviously means that it's a vector. Okay, so in this case, m is the mass of a body in kilograms. G is the acceleration due to gravity near the surface of that body in meters per second squared. But I also have that G is also the gravitational field strength around a body. We will study gravitational fields in detail, and I will show you, and you can actually prove to yourself right now, that a Newton per kilogram has the same basic SI units as meters per second squared. And of course, weight, because it's a force, it's a vector quantity, and its units are newtons, okay? Remember that mass is the same for an object anywhere, but its weight varies because the force of gravity varies according to where it is in the universe, okay? So this very interesting table here shows you the acceleration due to gravity, which is a crucial part of the weight equation, on different planets in the solar system. It's very, very interesting. And I want you to notice that all these values are multiples of Earth's values, okay? So Earth is 1 straight across. It's also showing the radius and the mass. And I want you to think about if there's a pattern in the acceleration due to gravity for different planets if you look at the mass and the radius. Okay, maybe pause the video and study these values and see if you can notice some sort of pattern. Okay, in the case of an object near a planet, the force of gravity is always directed towards the center of the planet, and I have here in the negative r hat direction, which I'll explain in just a minute. As you get farther away from a planet, the weight vector, the force of gravity, actually decreases. Okay, so clearly, as r gets bigger, the force of gravity has to go down. Okay. Now it's also true that more massive objects have a greater force of gravity. They weigh more than less massive objects. So therefore, the weight must be proportional to the mass. And as we saw, W equals mg, so that's correct. Notice that W equals mg, the previous equation for weight, does not take into account the distance from the center of a planet or a massive object. Okay. So let me show you what I mean by this negative r hat thing. Okay. Well, first of all, the force of gravity is proportional to the mass of the Earth, or it's also proportional to the mass of the object, and it turns out it's proportional to 1 over r squared. Okay, we may have gone over this previously. So I can put these proportionalities all together and say that the force of gravity is proportional to the mass times the mass of the Earth over the r squared, where r is the distance between the actual mass and the center of the Earth. Okay. Putting this all together, I get this equation called Newton's law of universal gravitation. Okay. Which is g mme over r squared, where g is the universal gravitational constant. I don't want to talk too much about that, but what I want you to realize now is just understand how these are related, okay? How these variables are all related and how they're proportional to one another. Again, I want to talk about where this negative r hat comes from. Remember when we talked about unit vectors, I hat, j hat, k hat, in the x, y, and z coordinate axes respectively? We said that those were unit vectors of length 1 unit pointed along those axes. Well, there's another unit vector that's very important, and it's called r hat. And it's the unit vector pointed outwards radially from a point in all directions. Okay, so it's kind of like unit vectors that trace out a sphere in 3-dimensional space. Okay, so in this case, if this, whatever scale I'm using, if this red vector indicates 1 unit, okay, that's the positive r hat direction acting outwards. If you have something acting inwards towards the center of a sphere, for example, that would be the negative r hat direction. That's where negative r hat comes from. And remember, in any equation, if you have a vector quantity on the left-hand side, there has to be something on the right-hand side that's also a vector quantity, or else it's not going to be a proper equation. It's not going to be one vector quantity equals to another, okay? So that negative r hat, that's what makes everything on the right-hand side of this equation a vector quantity, okay? And of course, W equals negative W times R. Notice the bold and the vector notation, which is mg, okay? This relationship right here implies that a graph of the weight or the force of gravity on an object, when plotted against the distance from the center of the Earth, would go down as 1 over r squared. We will study this graph later. And in fact, this data here is for the International Space Station, which has a mass of 6.38 times 10 to the 6 meters. Okay. Now, what this means is that every object in the universe exerts a gravitational force on every other object in the universe. We simplify this and we generally say that weight it's a statement of Newton's law of universal gravitation, but it's really, when we think of weight, we think of our force of gravity like on us, on my mass, for example, relative to the Earth, because the Earth is so much more massive than me. So that's kind of how we define it in terms of a planet, because that's what we're familiar with, okay? Okay, second kind of force that we deal with a lot is tension. And what tension is it's a force within a body when it's stretched. The variable for tension is a vector quantity big T, okay? So in a string, tension is from pulling on both ends. So if you pull on both ends of a rope, you get tension. So in this case, look at this diagram carefully. If we define up as positive and down as negative, on this end you have a negative tension, and on this end you have a positive tension. But at every single point in the rope, there's a tension acting. It depends on what direction the rope is actually pointing. And often we idealize a string or a rope by assuming that it's massless. So for example, in this case, if we don't consider the rope to be massless, well, there's more mass down here than there is up here, so actually the tension would not be constant throughout. So we neglect the mass of the string or the rope, and we just say that the tension is the same throughout, okay? So in this case, if you're pulling in this direction, whether you're pulling at the end of the rope or right on the hook on the box here, it's the same tension. You could be pulling with the same tension. The rope doesn't know. You could be actually either having a box sitting there, or having someone pull exactly the same tension in the other way, assuming that the box is not moving, okay? A string or a rope that's not this term taut has no tension at all, okay? So here are a couple of other examples of how we would draw tension and weight vectors on various objects, okay? And I want you to note that tension acts in both directions in a string or rope, and we usually indicate one is positive and the other is negative, okay? Now, the case of a spring, springs are really important for us in physics, and we're going to spend a lot of time playing around with them, okay? In a spring, the tension is called the restoring force, and we'll study this more later. We're going to do a lab actually with springs where we deal with restoring forces and tension. It's given by Hooke's law, named after a scientist named Hooke in the 1600s. And Hooke's law simply says that in a spring, F, the restoring force, which is actually T, which is actually the tension, is negative K times the displacement, okay? And X is given by the displacement. The negative sign comes from the fact that the force, that the tension, and the displacement are actually in different directions, and I'm going to show you what I mean by that. Okay. All right. So in this case, when the mass is going up, there's a force being applied to it, and there's a tension going upwards. Okay. All right. Notice that the displacement is getting smaller when this upwards force is being applied. Hence the negative sign. And of course the acceleration is also going up when the net force is acting upwards. When it's going downwards, okay, the force is acting downwards, tension downwards, and the actual mass is accelerating downwards in simple harmonic motion. It's restoring because it's always acting to bring the mass back to its equilibrium position, which is its natural length here, okay? Okay, so again, when you compress a spring, there's a force in it, a tension that pushes opposite to the direction in which it's been displaced. There's your negative sign. When you stretch it, the restoring force is acting in this direction, seeking to bring this end back to its equilibrium position, which is in the opposite direction from its displacement in this case. Okay? So we'll study more about springs, and we'll talk more about springs later. The spring constant K is simply a measure of the spring's stiffness, all right? And then we'll do some demos on this in class. Okay, another kind of force, normal forces. It doesn't mean that every other force we've studied is abnormal, obviously, but normal means something that's perpendicular to something else. These are also called contact forces. And we denote the normal force by little n hat, okay, or F sub n, okay? And what this is this is the reaction force of body B on body A when body A touches body B, all right? If this reminds you of Newton's third law, that's what Newton's third law is all about, which we're not really talking about explicitly yet, okay? So n hat is the unit normal vector that's perpendicular to a surface. So for example, you have a cinder block on a table. There's a weight acting downwards of the cinder block. If the cinder block is not accelerating in the frame of reference of the table, there must be an equal and opposite force acting upwards. Well, that's the normal force, and the magnitude of F sub n here equals the magnitude of the weight in this case. Okay? Now, if I were to push down on the cinder block with 11 newtons and its weight is 15 newtons, that means that the normal force actually increases to 26 newtons because the net force downwards is now 26 newtons. And again, the cinder block is not moving. It's not, its change in velocity is 0. Okay? All right. If I were to lift up on the block, again, the normal force would then change, okay? If I lift up with 11 newtons, then it means that the normal force is actually 4. Now, if I lift up with, say, 16 newtons, there is no normal force because the contact between the cinder block and the tabletop has been lost, okay? When the surface is curved, the normal force is still perpendicular to the surface on a molecular level, okay? All right. Now, frictional forces, really important kinds of forces. We deal with these all the time in virtually every single thing we do throughout life, okay? Frictional forces are usually given by a lowercase f because they're so common, and we differentiate them from the uppercase f, which refers generally to other kinds of forces. And a frictional force is any force that opposes the motion of a moving body or keeps a stationary body at a constant velocity. Okay, and it happens whenever one body touches another. Okay, so for example, in case A, if you have a box on a table and you're pulling on a rope, okay, if it's not moving, then this frictional force here has to be the same magnitude as the force with which you're pulling. If you increase the force, then you're increasing the frictional force occurring in the opposite direction. If you are pulling with even more force, eventually the box will move, and in that case, it's a different kind of frictional force. There are different kinds of frictional forces depending on whether an object is moving or whether an object is stationary, okay? So the frictional force acts parallel to surfaces, two surfaces in contact, and is determined by the types of surfaces, okay? So for example, if you have Ice sliding along ice, okay? This thing called the coefficient of friction, which gives you an indication of how much friction there is. Ice on ice would be very low, okay? Other things, steel on steel would be a little bit more, okay? If you really want to get a lot of friction, what you would do is you would use like rubber. Here you go, rubber on dry concrete. That's a relatively very high coefficient of friction. Or like sandpaper on rubber, or two sandpapers rubbing together. That's a lot of friction there, okay? So again, if things are not moving, we deal with static friction. If they're moving, we deal with kinetic friction. We will study these types of frictions in much more detail in a little bit, okay? Also note that the coefficient of static friction is always higher than the coefficient of kinetic friction. Again, what this really means is that it's harder to get an object moving than it is to keep an object moving when you take into account friction. But again, we'll talk about that later. Okay, drag forces. We've already talked about these kinds of forces. These are forces that oppose the motion of a body through a fluid, okay? Typically F sub D. It's really a frictional force. So in this case, a cyclist, the velocity is obviously in this direction. The greater the velocity, the greater the drag force, or the resistive force, which is really going in the opposite direction. It's always directed opposite to the velocity. The faster the body, the greater the drag force. Okay, this is a cool little experiment that we do that I've done in 9th grade before. And what we do is we take cooking oil and we put water droplets through it. You can probably see from this video that the water droplets are actually not speeding up. They're not accelerating. So if that's the case, then the drag force upwards has to equal the weight of the drop, or in other words, the magnitude of the drag force equals the magnitude of the weight, okay? Only if it's not accelerating, okay? So again, we've gone over this before, the difference between the drag force for smaller speeds and greater speeds. And at this thing called terminal velocity, we found that terminal velocity is mg over k, where k is a constant that depends on the nature of the fluid and the object moving through it. Okay, so again, we've gone over this in previous videos. Okay, buoyant forces. You deal with this a lot if you spend time on the water, sailing, fishing, boating, whatever. And a buoyant force is the force upwards on an object that's placed in or on a fluid. Sometimes it's called upthrust, okay? So, if the buoyant force is equal to the weight, the object will float. If the buoyant force is less than the weight, okay, then it will sink, okay? And that's that. I mean, pretty straightforward, right? Note that the object does not need to be on the surface in order for the buoyant force to equal W, the weight, for example. So here's a case of a container ship that's on the surface. Here's a jellyfish that's sort of suspended in the water. Okay, the buoyant force is equal to the weight if it's not accelerating up or down. Same thing with the container ship. The only difference here is the jellyfish is in the ocean and the container ship is on the ocean. Okay, I'm going to talk about free body diagrams now real quick to end this video. Super important, super important. You got to really pay attention to the next couple of slides, okay? We use these things called free body diagrams, and what they do is they show the magnitude and the direction of all forces acting on a body. And I'll give you some examples. So often the body is in the middle of the diagram at the center of a coordinate system. And sometimes you don't even need to draw the object, and only the forces acting on the object are shown to scale. You keep things, it simplifies things. You draw each body separately, and only the forces acting on that body, not the forces that the body exerts on something else. And it's really important to draw them completely and accurately. So you should choose a scale and draw things at the right angles, vectors at the right angles, and so forth. So really what free body diagrams they're vector diagrams. Okay, for example, you have two people pushing on a car, one 275 newtons, the other 395. The car would be pushed in this direction, but it has a frictional force of 560 newtons. Would the car move to the right or not? Okay. It turns out that when you draw a free body diagram, this becomes immediately apparent, and you draw your vectors to scale. Okay. So here's your resistive force, your frictional force right here going to the left. Your two forces going to the right in this direction. Notice how the car is not drawn. It's just a dot at the center of a coordinate system. The net force on the car is 110 newtons positively. So therefore, the car moves to the right. It actually accelerates to the right. If we knew its mass, we could figure out the acceleration from Newton's second law, F equals ma. So see the difference between a drawing and a free body diagram. Okay. So the first example here, what I want you to do is, for each of the following pictures and diagrams, I want you to draw a corresponding free body diagram. Okay, so pause the video and try this one before I show you my vector diagrams. Okay, for the box resting on the floor, pretty simple. Here's the box. I have a normal force acting upwards, and I have a weight acting downwards, and I've shown the vectors the same length but opposite directions, and I've labeled them properly. ladder leaning against the wall. Okay, the black thing here indicates the ladder. I have the normal force and the weight, and then I have a force action-reaction pair, if you want to think of it that way, of the ladder leaning up against the wall. Notice the lengths of the vectors are the same for each vector pair. Mass hanging on a string, and remember, none of these things are actually moving. Okay, so here's my mass. I have a tension force acting upward in this case, equal and opposite to the weight. And finally, one sphere in a Newton's cradle. Okay, so I have two strings that are holding up a mass right here at a certain angle. Here's the angle right here. And I'm calling one tension 1 and one tension 2. Notice the symmetry of the situation. You have a vertical line going straight down through the mass. These two angles are the same, and we use symmetry a lot when we're solving free body diagrams and finding net forces on objects.